Hello everyone, Nina this. Welcome to the second episode of our linear algebra video series. In this video, we will talk about matrices and explore their applications in solving linear equations. As before, let's begin with the history of matrices. Matrices are rectangular arrays of numbers. They trace back to ancient China around the 2nd century BC, where they appeared in the famous 9 chapters of the mathematical art. The Chinese used the matrices to solve systems of 3 equations with 3 unknowns by working with their coefficients. Matrices were used as short forms for systems of linear equations. In 1693, Leibniz introduced the notion of a determinant, marking the beginning of the modern study of linear algebra. But back then, people didn't know his investigation. Later, the renowned mathematician Euler observed that systems of equations might not always have unique solutions. He realized that certain conditions needed to be added to ensure uniqueness, although he didn't provide these conditions himself. Gauss introduced the Gauss animation in 1811 when he invented the method of least squares for solving systems of linear equations. However, during that period, matrix notation was not yet used. The term matrix was first used by Sylvester in 1850. Later, Cayley formally introduced n-by-n matrices in his papers and defined crucial matrix operations like addition, subtraction, and multiplication. He also introduced concepts such as the identity matrix and the inverse of a square matrix. Additionally, he used the inverse matrix to solve systems of linear equations. As the years passed, matrices became an essential tool in various fields, including physics, engineering, computer science, and more. Now let's look into the concept of matrices. Typically, matrices and linear transformations are introduced together because matrices are also linear transformations. But covering everything in one episode would be too much, so we will leave linear transformations for later. In the rest of this video, we will cover these topics. Let's explore the basic notion of matrices. A matrix is an array of numbers, represented as Aij, where I is from 1 to m, indicating the row numbers, and j ranges from 1 to n, indicating the column numbers. The matrix has m rows and n columns, making it an n-by-n matrix. This n-by-n represents the size of the matrix. Each number within the matrix is called the entry. And we denote the entry in the ith row and jth column as Aij. For example, A12 is known as the 1-2 entry of the matrix. In our previous episode, we introduced the vectors. It's worth noting that any vector can be viewed as a matrix. A row vector corresponds to a 1-by-n matrix, and a column vector is an n-by-1 matrix. When m equals n, we call the matrix a square matrix. On the other hand, if all the entries in a matrix are equal to 0, it's a zero matrix, denoted by this. Matrix addition. When adding 2 matrices, they must have the same size. The resulting matrix is obtained by adding corresponding entries from both matrices. We can see the definition here. For example, if A is 2, 1, 6, 4, 3, 5, B is 2, 7, 1, 1, 5, 0, we can add these 2 matrices and get A plus B is 4, 8, 7, 5, 8, 5. Scalar multiplication. To multiply matrix A by a number alpha, we multiply each entry of A by alpha. We have the definition here. For example, if A is 2 minus 1, 1, 4 minus 3, 5, then 2A is 4 minus 2, 2, 8 minus 6, 10, and a half A is 1 minus a half, 2 minus 3 over 2, 5 over 2. We can also find the additive inverse of a matrix. The matrix minus A is obtained by multiplying each entry of A by minus 1. In other words, minus A is minus Aij. The additive inverse matrix satisfies the property A plus minus A equals 0. where 0 is the zero matrix. For example, if we consider the same matrix A, 2 minus 1, 1, 4 minus 3, 5, then minus A is minus 2, 1, minus 1, minus 4, 3, minus 5. Matrix multiplication. Similar to matrix addition, there are certain restrictions for matrix multiplication. First, let's state the basic definition. We can use the sizes of matrices to determine if multiplication is possible. For example, we take these two matrices. A is 2, 1, 5, 1, 0, 1, and B is 2, 2, 1, 1, 3, 2. A is a 2 by 3 matrix, and B is a 2 by 3 matrix. The number of columns in A is 3, and the number of rows in B is 2, which are not the same, so we can multiply these two matrices. When we need to check whether two matrices can be multiplied, we can simply compare their sizes. If the number of columns in the first matrix matches the number of rows in the second matrix, then multiplication is possible. The size of the resulting matrix will be determined by the other two numbers. Now let's multiply two matrices. The main idea is multiplying row by column. Let A be 2, 1, 5, 1, 0, 1, and B be 3, 1, 2, 3, 1, 1. We first check the size. A is a 2 by 3 matrix, and B is a 3 by 2 matrix. Since these two numbers are the same, we can multiply them, and the resulting matrix will be a 2 by 2 matrix. Now A times B is calculated as follows. A times B equals this, which can be simplified to 13, 10, 4, 2. We can observe that the first row of matrix A and the first column of matrix B gave us the 1, 1 entry of the resulting matrix. Similarly, the second row of matrix A and the first column of matrix B gave us the 2, 1 entry, and so on. You can use these tips to check if you obtain the correct answer. A quick note before moving on to the next section. Matrix multiplication is not commutative, so in general, AB is not equal to BA. We can quickly prove this by providing an example, like the one shown here. Inverse matrix. Unlike numbers, where we have 4 operations, matrices do not have a division operation. Instead, we use the concept of the inverse matrix. Before discussing the inverse matrix, let's define an identity matrix. An identity matrix is a special type of square matrix that acts as the multiplicative identity for matrices, similar to how the number 1 acts as the identity element in number multiplication. The proper definition can be seen here. If we have an n by n identity matrix, all its diagonal entries are 1, and the rest are 0. When we multiply any non-identity n by n matrix by the identity matrix, we get this non-identity matrix itself. We use square matrices to define inverse matrices. Let A be an n by n matrix. Then the matrix B is said to be the inverse matrix of A if BA is AB equals I, where I is the identity matrix. We use A inverse to denote the inverse matrix of A. We can use this definition to determine if a matrix is the inverse matrix of another. For example, if A is 1, 2, 3, 4, and B is minus 2, 1, 3 half, and minus a half, then is B the inverse matrix of A? It is. We can show it by doing the following calculation. A times B is 1, 0, 0, 1, which is the identity matrix, and B times A is also 1, 0, 0, 1. So B is the inverse matrix of A. But not all matrices have an inverse. One of the methods requires us to use the determinant of a matrix, which will be introduced in later episodes of this series. Today we will use Gaussian animation, also known as row reduction or Gauss-Jordan animation, to determine whether an n by n matrix is invertible. Gaussian animation is a process used to transform a matrix into echelon form. In our previous video, on modern methods for solving systems of linear equations. We introduced echelon form and row operations. If you need a recap, please follow the link which is there or in the description below. Now let's see how to obtain the inverse matrix using Gaussian animation. We start with matrix A. A is 1, 2, minus 1, 0, 1, 1, 0, 2, 7. First, we write down the augmented matrix, where A is on the left and the 3 by 3 identity matrix I3 is on the right. We draw a vertical line to separate A and I3. Next, we apply Gaussian animation until we get the reduced echelon form of A on the left and another matrix on the right. If the matrix on the left becomes the identity matrix, then the matrix on the right will be the inverse matrix of A. If the left matrix doesn't become the identity matrix, then A is not invertible. This means that we can use Gaussian animation to check whether a matrix has an inverse. Now let's perform row operations. First, we change R3 into R3 minus 2R2. Then R3 becomes 0, 0, 5, 0, minus 2, 1, and the rest of the rows remain the same. Next, we divide R3 by 5 and get 0, 0, 1, 0, minus 2 fifths, 1 fifth. Then we change R2 into R2 minus R3 and get 0, 1, 0, 0, 7 over 5, and minus 1 fifth. Finally, we focus on R1. We first change R1 into R1 minus 2R2 and get 1, 0, minus 1, 1, minus 14 over 5, 2 fifths. Now we need to remove this minus 1 from R1 by performing R1 plus R3 and get 1, 0, 0, 1, minus 16 over 5, 3 fifths. The matrix on the left is the identity matrix, and as a result, the matrix on the right is the inverse matrix. Therefore, we have successfully obtained the inverse matrix using Gaussian animation. That's all for this episode. On this channel, I will also update other video series and run Study with Me streams during weekdays. You can find my schedule there. The next video on linear algebra will be uploaded after the next one on this channel. If you want to learn more about linear algebra, don't forget to subscribe so you won't miss the next episode. Thanks for watching. I will see you in the next video.